In Volume 1 we saw the Cartesian equation for a straight line in 2D Cartesian space. In this video we're going to look at how we can use vectors to represent a straight line in 3D Cartesian space. Now by representing a straight line with vectors, we're then able to apply all our various vector operations to the vectors that represent that straight line. And thus we have a powerful toolkit of operations for solving problems involving those lines. Now in the next video, for example, we're going to see how this representation of a line makes it easy to find the perpendicular distance of a point from a line by applying all the various vector operations and theories that we've seen so far in this DVD. Now when we found the equation for a line in Volume 1, we said that a straight line is explicitly defined by 2 points. There's only a single straight line that will ever join two specific points in 2D Cartesian space. Well, the same applies in 3D space. If we have 2 points in our 3D space, there is only a single line that will join these 2 points. So if I had 2 points in 3D space, there's only a single line that would join these points. So let's say that I had a point P1, and this point has the coordinates 2, 3, 1, and I have a point P2, and this point has the coordinates 4, 5, and 7. Whether these points exist in 2D space or whether they exist in 3D space, there's only ever a single line that would connect those 2 points, that would pass through those 2 points. But how can we represent these points using vectors? Well, we've seen how to represent points using vectors. We can use position vectors. So if we have our 3D scene and we know somewhere in our 3D scene is the origin. So there's a point in our 3D scene that has the coordinates 0, 0, 0, and it represents the origin of our 3D scene. And we know that a position vector is a vector that starts at the origin and travels to some point in space. So we could represent each of our points, our point P1 and our point P2, using vectors by representing them with position vectors. So we could create a position vector that represents P1 and a position vector that represents P2. So if we had a position vector that represents P1, we could call this position vector lowercase p1, and this of course is a vector. And if we had a position vector that represents P2, we could call this lowercase p2, and of course this is a vector, and we know that P1 is going to be equal to the vector 2, 3, 1, because it travels from the origin 0, 0, 0 to the point P1, which is 2, 3, 1, and we know that P2 is going to be the vector 4, 5, 7, because again it travels from the origin 0, 0, 0 to the point P2, 4, 5, 7. So we've represented our points using vectors, but how can we represent our line using vectors? Well, we could construct a vector that travels between our 2 points. So I could construct a vector that travels between our 2 points, and we could call this vector, I don't know, let's call it vector D. We know that by using our position vectors, we can find this vector D that travels between the 2 points, and we've seen how to do this already. We've seen that I could say vector D is equal to, well, if we're starting at point P1, we need a negative P1 and then a positive P2. So that's the same as saying P2 minus P1, which if I scroll down, we know that that is equal to 4, 5, 7 minus 2, 3, 1, which is equal to 4 minus 2 is 2, 5 minus 3 is 2, and 7 minus 1 is 6. So our vector D has the components 2, 2, and 6. But this doesn't represent our line. It does represent the direction between our 2 points. It also represents the distance between those 2 points. But it doesn't represent the line that travels between those 2 points, because D is just a vector. D is not a position vector. It doesn't start at the origin. We haven't defined it as a position vector. D is simply a vector. It's free to float around our Cartesian space, and that means that although D could start at P1 and travel to P2, it could be down here, it could be over here. They're all valid vectors D because D simply has a direction and a length. So we need some way to lock D in place. We need some way that D is locked in place so it represents our line. Now we can do this by using one of our position vectors. So if I was to define some point in space as being a point P, so we have a point P1 and we have a point P2, and those points are defined by position vectors. Well, if I was to have some other point in space that I'm going to call the point P, we could define P by using a position vector, which would be lowercase p. So there's some point in space, we don't know its coordinates yet, but that point in space P is represented by the position vector P. So that means wherever that point in space is, we're representing it by using a position vector that's called P, but we don't yet know where in 3D space that point is. Well, if we've got that point P, what if we said that was equal to our position vector P1, so it's a position vector that we're defining, P, so we know we start at the origin, and starting from the origin, what if we say we travel from the origin along P1, and then travelled along in the direction of D. So we could say P1 is, or rather P is equal to P1 plus D. What we're saying is we're taking a position vector, that means we start at the origin. P is a position vector because that's how we're defining it. We're saying P is a position vector. So that means we're starting at the origin, we're locked in place at the origin, and starting from the origin we travel along P1. So we travel out here to the point P1 because we travel along position vector P1, and then we travel along D. But this still doesn't actually represent our line. We're getting close, we're travelling out to our line and travelling along our line, but actually P1 plus D is going to take us from the origin along P1 and then along D. What it's actually going to give us is the vector P2. It's going to give us this point in space, because if we started at the origin and travel along to P1 and then travel along the length of D, that is going to put us right here at P2, which means in vector form we're going to look like P2. Now I can prove this if we actually evaluate this equation. So we're saying P1, which we know is 2, 3, 1, plus D, which is 2, 2, 6, which is equal to 4 in X, 5 in Y, 7 in Z, which we can see is equal to P2. So if P is equal to P2, the position vector P2, then we know the position of the point P is going to be equal to, so our point P as represented by position vector P is equal to 4, 5, 7, which is equal to the point P2, because we know that the point P2 is 4, 5, 7. So we're getting close. Again, we're starting at the origin, we're travelling along P, and then we're travelling along the direction of D, but we're not quite there yet. What we need is some way that we start at the origin and travel along to our start point P1, and then travel some distance along D. We don't want to travel the entire length of D, we want to travel some distance along D, but ideally we want to travel some variable distance along D, so that if we travelled a little way, we get a point here on the line. If we travelled further, we get a point here on the line. And if we kept on travelling, we'd infinitely extend our line and have points all throughout our 3D space that exist on that line. So how are we going to travel some variable distance in D? Well, what if we travelled along the length of P, or rather the length of P1, from our origin along the length of P1, and then travelled some scaled version of D. If we scale D, we know we're going to keep the same direction, which means we are going to be travelling along our line, but we're going to change the distance, which allows us to travel to various points along that line. So instead of the equation P is equal to P1 plus D, what if we had the equation P is equal to P1 plus T multiplied by d, where t is some scalar parameter. So because t is a scalar parameter, we can scale the length of d, and that means we travel from the origin up p1, because we're saying it's equal to p1, plus some scaled version of d, which means if we had a small scale version of d, we get a point here. If we had a longer version of d, we'd end up with a point here. And because our parameter t can take any value, we can represent any point on that line. So let's take a look at that. Let's actually look at some examples of using this. So what we're saying is that we're going to be controlling the position of our point on the line by using that parameter value t. So let's say that t was equal to 0.5, for example. Well, then we get that p is equal to p1 plus 0.5 times d. So that means that p is equal to, well, p1 is 231. 231 plus 0.5 multiplied by d. d, as I scroll up, d is 226. So d is 226. So this is going to be equal to 231 plus 0.5 multiplied by 2 is 1. 0.5 multiplied by 2 is 1. 0.5 multiplied by 6 is 3, which is equal to 2 plus 1 is 3. 3 plus 1 is 4. And 1 plus 3 is 4. So p, the position vector p, is equal to 3, 4, 4. Therefore, the point p is equal to 3, 4, 4, because we start at the origin, p is a position vector, and we travel 3 in x, 4 in y, 4 in z, so that means we're going to end up at the point 3, 4, 4. Now on our diagram, the point 3, 4, 4 would be right around here. And why is it right around here? We've used a parameter value for t of 0.5. That means we've taken our vector d and we've scaled it by a half. It's now half the length that it originally was. That means if we travel from the origin along to p1 and then travel along half of what used to be d, we're going to end up halfway between the point p1 and the point p2. So because we used the parameter value t is equal to 0.5, we ended up here halfway between p1 and p2. So let's try that with some other parameters. So I'm going to clear some space. And I think what I'm going to do is reuse some of the workings that we already had here because I'm running out of whiteboard. So I'm going to say that p is equal to p1 plus t times d. We know this already, but I'm going to say what happens if we use the parameter value of 0.25 for d. Well, that would mean we get that p is equal to p1 plus 0.25 times d, which means p is equal to 231, which is p1, plus 0.25 multiplied by d, which was 226, which means, as I erase these, and these, which means we're going to get that p is equal to 231 plus 0.25 times 2 is 0.5. 0.25 times 2 is 0.5. 0.25 times 6 is 1.5. So 2 plus 0.5 is 2.5. 3 plus 0.5 is 3.5. And 1 plus 1.5 is 2.5. So if that's what p, the position vector p, is equal to, our point p is equal to 2.5, 3.5, 2.5, and we know on our diagram that's going to be right around here because we said t is equal to 0.25. That means if we had d, we've now scaled it by 0.25, that's a quarter, so it's now a quarter of the length that D was originally, and we're saying we're having a position vector, we're starting at the origin, we're travelling along the length of P1, and then we're adding on to that a scaled version of D that is a quarter of the length. So that's going to give us this point right here. So let me just erase this. Now let's look at another example before we move on with some more theory. So in this case, what happens if we use a negative value for t? What happens if I said that t was equal to -1? Well, that means if p is equal to p1 plus t times d, then p is equal to p1 plus -1 times d, which means p is equal to the vector 2, 3, 1 plus -1 times the vector 2, 2, 6, which means, as I erase these, and these, fantastic, we're going to get 2, 3, 1 plus -1 times 2 is -2, -1 times 2 is -2, -1 times 6 is -6, 2 plus -2 is 2 minus 2, which is 0, 3 plus -2 is 3 minus 2, which is 1, and 1 plus -6 is 1 minus 6, which is -5. So the position on our line, the point on our line is 0, 1, -5. And where is this on our diagram? Well, actually, it's right over here at the edge, probably a little bit further, but I've run out of whiteboard, because we've taken a vector d. Now I'm going to draw a smaller version here just so that I can fit it all in. So we've taken our vector d and we've multiplied it by a scalar value t that was -1. Well, we know the effect that that's going to have. It's not going to change the length of d, but because it's negative, d is now going to travel in the opposite direction. We've effectively created minus d. Now again, because it was -1, we've not changed the length because we're scaling by 1, but because it's minus, we have reversed the direction. So that means starting at the origin, we're traveling along P1, and then from the point P1, we're traveling in the opposite direction of D, but for the length of D, which approximately, if that's the length of D, is going to take us approximately over here, giving us, as I hide out everything that just popped up, don't mind me, giving us this point out here. So even if we use negative values, our equation still works. And instead of giving us points in the direction of D from P1, it's going to give us points in the opposite direction, allowing us to create points anywhere along our infinitely long line. So we've seen that we had this equation. I'm going to rewrite this on the whiteboard here. We had this equation that P, which is a position vector, is equal to P1, which is a position vector, plus T multiplied by D, which we can think of D as our direction vector. And what we're saying is that a point on the line, as represented by the position vector P, is equal to travelling from the origin along P1 and then travelling some distance along D. And by changing that parameter value t, as we've just seen, that's going to allow us to move in the positive direction of D with a positive value of t. The larger t is, the further we move. Or we can move in the negative direction of D if we have a negative value of t. Again, the larger the absolute value of t, the larger we scale up D, but in the opposite direction, and therefore the further that we move. Now, using a parameter to represent a point on the line is actually extremely useful if we're solving problems. So the first thing we can see is if we look at our equation, we can actually see that if we had a parameter value of 0, that's going to give us the point P1. So if t was equal to 0, we'd get P is equal to P1 plus 0 times D, which means P is equal to P1. So on our earlier diagram, that gives us this point P1. We're saying we start at the origin right here and we travel along the position vector P1, thus that's going to give us the point P1. So we get the point P1 when t is equal to 0. T is equal to 0 is giving us that point right there. We can also see if t is equal to 1, then our equation becomes p is equal to p1 plus 1 multiplied by d. Therefore, p is equal to p1 plus d, which we've already seen, but I will work through this. If p is equal to p1 plus d, then we have already seen that we travel from the origin along P1 and then along the entire length of D. Thus, that's the same as travelling along P2. We know this because we start at the same point, end at the same point. So that means that when we have a parameter value of 1, it's the same as travelling along P2, which means we're going to get this point here, which is P2. So when t is equal to 1, we're going to get this point right here, and we can finish off our earlier equation that we were writing to say that p is equal to p2. So we can see with a parameter value of 0, we get the first point, the start point, if you will, that we use to define our line. And with a parameter value of 1, we get the end point that we used to define our line. Now, to understand why this is useful to us, as I bring back my earlier diagram, to understand why it's useful that we know a value of 0 gives us this point and a value of 1 gives us this point, let's consider one of the problems that we might use the vector equation of a line for. Let's say that we're intersecting a line with some piece of geometry and we're representing that line with the vector equation. So let's say we're intersecting a line with a plane, for example. Now in this DVD we're not actually going to look at how we'd calculate that point of intersection, though with all the theory that we have covered in this DVD, you're going to have all of the groundwork there to easily be able to research this on your own. But anyway, if we were solving the equation for the point of intersection between a vector representation of a line and a plane, logically what we're going to be solving for in that equation, if I scroll down to find my equation, here we go. What we're going to be solving for in that equation is t. Because if we're trying to find the point of intersection, we know that P1 is a constant value, D for our line is a constant value, T is the only thing that changes to change our position on the line. T controls the position along the line. Therefore, to find the point of intersection, we'd be trying to find the parameter value of T at that point of intersection. So let's say we've solved that problem, we find the point of intersection, and we've got back some value of t. So we have some value of t that represents the point where that intersection occurs. Now that's fine if we were intersecting an infinitely long line, so a line that extends forever in both directions with that plane. We'd simply want to make sure, is there an intersection, and if there is an intersection, we could find the point of intersection. But let's say we weren't intersecting an infinitely long line. Let's say that we were intersecting a line segment, a small segment of the infinitely long line that we know travels between P1 and P2. So that means if our plane was out here and our infinitely long line did intersect it, we're not interested in that because it's not the line segment that intersected it. Or if our plane was out here and our infinitely long line intersected it, we're not interested in that because our line segment didn't intersect it. We're only interested if the line segment itself intersects our plane. Well, by solving for this parameter value t, and knowing that t equals 0 at the start point of our line segment and t equals 1 at the end point of our line segment, we can check this parameter value t. Because if the parameter value t is between 0 and 1, we know the point of intersection is on this line segment. It's on the line segment that travels between P1 and P2. Because we know we start with a value of t equals 0, and as we increase t, we're going to end with a value of t equals 1. Therefore, if the point of intersection is represented by a parameter value between 0 and 1, we know we have intersected on this line segment. However, if our parameter value is less than 0, i.e. it's a negative value, we know once we'd reached P1, we're travelling in the opposite direction of our vector d. That means if the parameter value t is less than 0, we're somewhere on our infinite line before we get to the point P1, so we can disregard that point of intersection because we've not intersected the line segment. And if our value of t was greater than 1, then we know we have travelled further than P2 along our line. And again, we can disregard that because the intersection wasn't with the line segment. Now, another use where this parameter would be useful is in a ray tracer, for example. So if we had a ray tracer and we've got a number of rays in that ray tracer that we're firing into our scene and we want to intersect with some objects, if we represented those rays using a vector equation representation of the line, then what we could do, we could intersect each of those rays, each of those vector equations with our objects in the scene. So let's say we're taking one ray in particular and we've intersected it with all of the objects in the scene. We found the points of intersection between that ray and any objects it does intersect. What are we going to get back for those points of intersection? We're going to get back parameter values for t. So we have a number of parameter values for t, and let's say that we intersected one object and it said we had a t of 1.5. We intersected another object and we had a t of 0.7, and we intersected a third object and we had a t of 3. Now, the interesting thing in a ray tracer, of course, is that if we fire a ray into a scene, what we're really interested in is the first object that we hit. If we are firing a ray and that ray is representing a beam of light as if we are looking into our scene, then the first thing that we hit is the first thing we see, and we won't necessarily see anything behind that. If it's an opaque object, we can't see through it. We're just going to see that object. But how could we find out which object is the first object we intersected? Well, if we say our ray is starting from P1 and travelling in some direction, and we represented it using our vector line equation where we travel from the origin up to P1 and then down the length of our ray. So let's say we were looking into the scene, we were looking using a camera, then P1 perhaps was the start position of our camera, the position of our camera, and D is our ray as it fires from the camera into the scene. Well, if we start our ray at point P1, we know as the ray travels from our eye, from our camera into the scene, it's going to be travelling in the positive direction of D. That means when we start at the camera, we have a parameter of 0, and the further we travel into the scene, the larger this parameter value is going to be. So that means very quickly, after I've found the points of intersection, I can actually find the closest object we've intersected, because that's the object that has the smallest parameter value. I can see as we travel from the eye, we started at 0, and as that parameter value gets larger and larger, we're traveling further and further into the scene, which means we intersected this object first at 0.7. Then as our ray continued further and further into the scene, we intersected this object at 1.5. And then as it continues further into the scene, we intersect this object at a value of 3. So by being able to represent a point on the line using parameter values, we know the relationship between those points. We know which is closer to our start point because it's going to have a smaller parameter value, and that can be incredibly useful to us. And there's actually yet another use, just throwing out examples here of uses for being able to represent a line using vectors and the power of having a parameter to represent a point on the line. Another use is actually we could find how far apart points on the line are. Now currently D is just a vector, it's not a unit vector, we haven't normalized it. D is just a vector, and that means our parameter t equals 0 gives us this point, and t equals 1 gives us the end point. And we know that could be useful for certain problems if we wanted to find an intersection, say, just on that line segment rather than an intersection on the infinite line. But what if we took D and we did normalize it? Well, if we normalize D, we'd get a unit vector, for example, D hat, which we know has a length of 1 unit. Now, if we started at the origin and travel along to P1 and then add 0 times D, we're still going to get this start point here. If we add 1 times D, if our parameter is 1, we're going to now move to the end of our unit vector. We're going to have travelled 1 unit along our line. If we added 2 times d, we'd add another d, if you will. We'd have scaled our unit vector up to twice the length, which means we would have travelled 2 units along our line. If we were to have added a parameter value of 3, so 3 times d, we'd have scaled d up to 3 units long, and thus we'd have travelled 3 units along our line, which means we can actually use that parameter value to measure distances between points on our line, because if we know that 2 points have a difference in parameter value of 1 unit, that means they are 1 length of d apart, which means they are 1 unit in 3D space apart. Likewise, if the parameter values were 2 units apart, for example, if we had t is equal to 1 and t is equal to 3, they are 2 units apart. That means they are 2 lengths of d apart. D has a length of 1 unit in 3D space. Therefore, they are 2 units apart in 3D space. So if we were finding points on a line and wanting to be able to measure the distance in 3D space between those points quickly, if we had a unit vector, then we know that our parameter values represent the distance that we're travelling. If we increase our parameter value by 3, for example, we have travelled 3 units. So that's another use of having a parameter value to control the position of points on the line. So the vector equation for a line is an incredibly useful representation for a line, and I've really barely scratched the surface for its uses. Now, as I mentioned earlier, in the next video, we're actually going to take a look at solving a problem where we use this representation of a line, and that problem's going to be finding the perpendicular distance of a point from a line, and that line is represented using this vector equation. Now, this is going to be an illustration A of how we can use this vector equation to solve a problem, but also how by having a line represented as a vector equation, we can actually apply all of our other vector theories that we've seen to help us solve that problem. So it's really going to help to bring everything that we've seen in this DVD together, which is why I chose that to be the concluding video of this DVD. But before we move on to the final video of this DVD, however, I would like to set just one question for you guys to work through on your own that relates to the vector representation of a line. So I'm going to bring up a new whiteboard. So if I bring up a new whiteboard, hide everything out. Fantastic. And this is question 1. And this question, I'm going to set you 2 points. There are 2 points in 3D space. A point P1 is equal to -2, 0, and 3. And a point P2 is equal to 1, -4, and 6. And there are 2 parts to this question, if you will. The first part of this question is I'd like you to represent the line that passes through those 2 points, the line that passes through P1 and P2, by using the vector equation of a line. Once you've done that, I'd then like you to find the position of the point on that line that is represented by the parameter value t is equal to 3. So using what you've seen in this video so far, I'd like you to represent the line that travels between the points P1 and P2, but using the vector equation of a line, and then I'd like you to find the position of the point on that line that is represented by the parameter value t is equal to 3. So if you pause the video and attempt to answer this question now on your own, and once you have a solution or if you get stuck, unpause the video and I'll work through the answer here on the whiteboard. Okay, welcome back everyone. So nothing more here than what we've seen so far in the DVD, or in this video in fact. So we know that P is equal to P1 plus T times D. This is our vector equation of a line. So what we need to do is we need to calculate P1 and we need to calculate D. Well, we know P1 because P1 is the position vector that represents point P1. So P1 is equal to the position vector -2, 0, 3. And we know we can also create a position vector P2 that represents our point P2, which is equal to, not minus, let's erase that, there we go, it's equal to +1, -4, and 6. And we know that we can find D based on these two position vectors. So if we're saying that D travels from P1 to P2, now I didn't explicitly state that in the question, which means if your D vector travels in an opposite direction, that's absolutely fine. It was more the method that I'm interested in here rather than the exact answer. So in my case, I'm going to make D travel from P1 to P2. You may have made D travel in the opposite direction as long as you've used a similar approach where you've used this equation, you found the position vector for one of the points, in this case I chose P1, and you find a vector that travels between those 2 points, and then we're going to plug that parameter value in. That's absolutely fine. So again, in my case, I'm going to say the vector travels from P1 to P2, and that means D is equal to P2 minus P1, which means it's equal to 1 minus 4, 6, minus 2, 0, 3, which is equal to 1 minus 2 is 1 plus 2, which is 3. Minus 4 minus 0 is minus 4, and 6 minus 3 is 3. So D, our direction vector, if you will, is 3 minus 4, 3, which means our equation here can become P is equal to P1, which is minus 2, 0, 3, minus 2, 0, 3, plus T multiplied by D, and D was 3 minus 4, 3. So in our case, this is an equation, a vector equation that represents our straight line. We're saying a point on the line as represented by the position vector P is equal to the vector minus 2, 0, 3 plus some scaled version using the parameter T of our direction vector 3 minus 4, 3. So now that we have that, to evaluate for a parameter T is equal to 3, we simply plug a value of 3 into this equation. That gives us that P is equal to minus 2, 0, 3 plus 3 times our vector D, which is 3 minus 4, 3. If we evaluate that, we get that P is equal to minus 2, 0, 3 plus 3 times 3 is 9, 3 times minus 4 is minus 12, and 3 times 3 is 9, which if we then evaluate that, we get that P is equal to minus 2 plus 9 is positive 7, 0 plus minus 12 is 0 minus 12, which is negative 12, and 3 plus 9 is positive 12. So the point in my example, the point on the line represented by the parameter value T is equal to 3, is the point 7 in X, 12 in Y, negative 12 in Y rather, and 12 in Z is the point 7, negative 12, 12 as represented by the position vector P. Of course, if you defined your direction vector differently, if yours traveled from point 2 to point 1, for example, or perhaps you even decided that you were going to normalize that vector and have it a unit in length, then of course the parameter value T is equal to 3 is going to give you a different result. But in my case, I constructed a vector that travels from P1 to P2. I didn't normalize that vector, and that meant that the parameter value of T is equal to 3 is equal to giving us this particular point, 7 in X minus 12 in Y, and 12 in Z. Now, of course, what I was interested in was the method here. As long as you understood the method and you took the same method, that's what I was looking for, as opposed to the specifics of the result that you got. Okay, so to recap everything that we've seen in this video, we first have seen the vector equation of a straight line, and we've seen that that is given by P is equal to P1 plus T multiplied by D, and if we're finding the line between 2 points, then we know that we can find D being equal to P2 minus P1. So we use the position vectors P1 and P2 to define the direction vector D that travels between those 2 points. We then multiply that by some scalar value, and if we add that to the position vector that gives us one of our points, we then travel from the origin to that point, and then some direction along the line that passes through that point. So this is the vector equation of a straight line. It's a very useful equation. It's a very useful reason to be using our vectors. And we're going to see, again, in the next video, we are going to see how we can use this to help us solve a problem and how that allows us to apply some of the other theories and some of the other operations that we can apply to vectors, how we can apply those to solve problems when we start representing the entities in that problem using vectors. It's also worth noting, of course, t here is our parameter that controls the position of the point along the line. That goes without saying. We've seen time and time again in this video how t does that, but if I'm concluding everything that we've seen in this video, then it is worth pointing that out. But that is everything that I wanted to cover in this video, and hopefully you'll join me in the final video of this DVD, the next video, where we're going to make use of this representation of a line to find the perpendicular distance of a point from a line represented by a vector. Thanks a lot, everyone.